So, welcome back. So I guess we had sort of one round of lectures on basic ideas and methods of nucleation. So from this point on, we're going to have lectures that will become either more biological or more focused on soft matter to a large extent. And the first talk in that series is by Dave Thirumalai from the University of Maryland, and he's going to be talking about aspects of protein folding and protein aggregation. And as before, make sure that you understand what he's saying and stop him if you don't.
And part sort of, what? You're the man, so. I don't know about the understand part, so we'll see how it goes. I actually, this morning, because I've been hearing some beautiful talks on nucleation, starting with David, and then this morning from Charasida, and some very nice stuff from Surajit, all seemed extremely impressive. I decided I was going to tell you about some tentative ideas on nucleation in the context of protein folding, and in fact you'll hear about this from some other viewpoint, I presume, from Giant Udganka tomorrow. I'm going to tell you some problems in protein folding, and really it's probably a testament to the fact that the problem is not easily stated. However, what constitutes a solution to the problem, or how do you even think about the problem, depends upon the practitioner. In fact, let me actually tell you, I will be talking about, unlike the very nice stuff that David talked to us yesterday about homogeneous nucleation theory, I think which has 100-year history or something like that, many of the things I'm going to tell you about are tentative and largely come from viewpoints that we and others have developed over the last some 20 years or so. And the guys who are responsible for that in my research group are these guys. He's a graduate student. He's now a postdoc with Chris Dobson in Cambridge. He was a student of mine. He is now a professor in the Korea Institute for Advanced Studies. She was a postdoc. She's just starting her job in Denison University. This is the guy whose work I talked a little bit before, and this is a talented graduate student who she's moving on to Columbia. And this person is going to take up a job in China in about 6 months or 4 months. A lot of people would say, is the protein folding problem solved? And my good friend Bill Eaton at NIH says, many have solved the problem as they have defined it. And this is roughly how it goes. So you define the problem as the way you see fit, and you can solve it, and that's the end of that. All the work I'm going to tell you about has been funded by NSF for about 20 years. There are many facets to the protein folding problem, and I'll sort of define what one generically might mean by the protein folding problem. One is to predict the three-dimensional structure of a protein, starting from an amino acid sequence, because Ann Finson taught us about 50 years ago that this is a self-assembly process, which means if you specify the environment and the sequence, it adopts roughly a unique folded structure whose architecture in principle is obtainable either by computations or more precisely NMR or X-ray crystallography. That's one aspect of the problem. There's a lot of interest in trying to design proteins and enzymes that could do reactions that are non-biological, and in this context David Baker has done some beautiful work in which he has designed enzymes that carry out organic reactions. There's a nice paper by him in Science not too long ago. The thing that I'm going to focus on today is, given that there is a relatively unique structure, how does the sequence sample the conformational space and get to the native state? And this is the mechanistic question that's underlying the approach to the native state. This is very much similar to the kinds of issues that we heard about. How does one phase nucleate in the presence of the other phase given appropriate conditions? In fact, I'll try to make an argument today, just for today's purpose, that there are some close analogies when viewed properly between the kinds of things we've been hearing about yesterday and today and the protein folding problem itself. Then there are issues about crowding effects, because in cellular conditions, the protein actually finds itself after synthesis by the ribosome in a very crowded environment consisting of other macromolecules like messenger RNA, ribosome, etc., and how does that impact folding? Are there fundamental differences between folding under in vivo conditions or in crowded environment as opposed to in vitro conditions where one studies this under near infinite dilution conditions? And I touched on a little bit the aggregation, and you'll hear more about this from an experimental viewpoint from Giant tomorrow. And there are fascinating questions about how do some proteins, or do all proteins in fact fold spontaneously as Chris Anfinson envisioned, or are there proteins that require chaperones? And in fact, there are a small percentage of proteins in both eukaryotes and prokaryotes which require molecular chaperones, and there are all kinds of molecular chaperones that exist, and this is an interesting topic in its own right. In all these problems and some more, folding in fact is at the center stage of the function itself, and therefore this has become a paradigm problem, much like maybe trying to understand the glass transition in the condensed matter community. Although, except for the plausible connection to aggregation and disease, many people thought in fact it is not really that important to understand the folding in detail, but now because of this relation to aggregation and hence to various neurodegenerative diseases, this has become of paramount importance. So we're going to just focus on the folding kinetics a little bit. On the experimental side, there have been a lot of developments, and I'll describe this a little bit. There's this protein engineering largely from Cambridge, coming from Alan Fish and company, and he's got a small school both in Cambridge and the rest of the world, whose sole job is to determine what are the nature of transition state ensembles as the protein actually folds, and I'll say very little about it. SACS and NMR are playing an increasing role in trying to understand the nature of the collapse transition that Giant actually talked about, I guess on Friday or Thursday, I don't remember, probably Friday. And I will get to some aspect of SACS at the end if I have time. Then there are these experiments. I'll not mention them at all. There are fast folding. You can ask questions like the enzymologist asked, what is the maximum rate at which an enzyme can operate? And so you could ask the question, what is the maximum speed limit? How fast can a typical protein actually fold? And in order to understand this, there were lots of very good experiments, both T-jump and rapid mixing, that have been devised both in the United States and in Japan. We already heard a little bit about FRET from Giant, but then the single molecule FRET, and I will show you some data on this in connection with the collapse itself and what does one actually mean by a formation of collapse state en route to the folding state. Supposedly, my next talk, if I get to, will in fact introduce you to this very fascinating topic, and I spend a lot of my time thinking about this, namely, how does one use mechanical force and understand the kinds of experiments that people like Carlos Bustamante, Steve Block, and others do, where a force is applied to two specific points on a biopolymer, or a biopolymer complex, or even a ribosome, and then from there, from the trajectories that you obtain by mechanically unfolding them, what can you learn about the underlying landscape? I might talk in the next hour. I'll spend some little time on this. On the theoretical side, and these are all things that happened only in the last 20 years, there have been a lot of work on using statistical mechanics on polymer ideas, some of which I'll describe today, in developing what's, I guess, come to be known as the energy landscape perspective of folding. And these have been supplemented by various kinds of simple-minded simulations, like lattice and off-lattice simulations, for which you can do exhaustive sampling that cannot be done by brute force molecular dynamics type simulations. And then there are MD simulations that continue to play a very, very big role, and I think in about 10, 20, 30 years, we'll be generating movies, as Charasita was telling us this morning. We'll be able to follow ensemble of folding trajectories that will go from the unfolded to the folded state. but I will certainly have retired, if not be dead by the time. So then there are bioinformatics and other things that we can think about. So if you read the protein folding literature, and you'll see these sorts of words that are actually thrown around: multiple folding scenarios, folding funnels, nucleation collapse, speed limit, designability, misfolding and kinetic traps, fold-ons, roughness, frustration, topological and energetic, transition state ensemble, phi values, prefactors, Cramer's theory, entropy barriers, glass transition laws, master equation, finite size effects, etc., etc. All these have now become part of the protein folding lexicon. They are meant to describe different kinds of phenomena, but the things that I'm going to talk about are in blue: nucleation collapse, in the spirit of the meeting, and just to keep our boss Sri happy. If he doesn't hear nucleation in a seminar, he'll probably kick us out. Kick me out anyway. And so then I'll describe some of these things as we go along. So if you want, this is a statement of the protein folding problem. This is one of my favorite proteins, which is a subunit of the so-called GROEL molecule, which is an E. coli chaperonin that is required to rescue some subset of proteins that cannot fold spontaneously. And this is the sequence. The structure of this in the 7-mer form was determined by the late Paul Siegler. And this is the whole sequence. It's about 549 amino acid residues. And one wants to know, given this sequence, how does one get to this structure, which can be partitioned into 3 domains that are given by three different colors. So that's a structure prediction, assembly mechanism, and that's a blue thing is what I'm going to describe today. So let's think of a much simpler problem, because the assembly of that previous sequence into that structure is extremely complicated to describe. But let's think about a protein which is, this is called a protein G. It's got just 56 amino acid residues. And the cartoon that one sort of thinks about to describe the folding process is you unfold this protein. You can unfold this either by raising the temperature, or you can add 5, 6, 7 molar urea, about 3 or 4 molar guanidinium chloride. It would unfold, and you would populate an ensemble of unfolded structures. And these ensemble of unfolded structures may or may not have persistent secondary structures. That's a question of debate that people are continuously engaged in. Because this is a starting point in the landscape for folding, one needs to describe the ensemble of these unfolded structures, and one thinks that the structure is both lost incrementally and probably gained incrementally. To anticipate what I'm going to tell you about a little bit, you could see that in this particular stage I've drawn this helix, and you might think of this helix, which is basically native-like, which means that its secondary structure looks exactly what it does in the folded state, might nucleate the rest of the structure. So that's one viewpoint on how this protein actually folds. So it is that viewpoint that I'm going to develop using series of hand-waving arguments. And before I do that, let's think about what kind of phases, if you wish, you would get in this protein folding problem. Long ago, Flory told us, and this long ago is 1948, that if I take a polymer, and this is something that Giant briefly described, and then you make the solvent good for this polymer, which means the interaction between the monomers of the polymer is more favorable to the solvent than interactions within the monomer, and therefore the polymer would actually swell, and that's what he understood, and he described a theory for how to predict the dimensions of such a polymer in a good solvent. Flory also knew full well that when you go below some temperature, which he called the theta temperature, the collapse temperature, then that's a temperature at which is a balance of interactions between the intrapolymer, monomer polymer interactions and monomer solvent interactions. They more or less cancel out, and the polymer undergoes a collapse transition. It becomes compact. If this were the only thing, then the problem is it can't be a protein, because one knows from rigorous polymer physics that the number of compact conformations scales exponentially with the molecular weight, but we know that the native state is relatively unique. And in the language of physics, you would say that there are some discriminating energetic interaction that says this helix should be next to this helix with the residues in this helix making specific contacts. Therefore, there's another phase transition, if you will, at a lower temperature, which I'll call the melting temperature or the folding temperature. One of the parameters, which I will not talk about today, that we introduced now nearly about 19 years ago, I think, is that if these two temperatures are pretty close to each other, collapse in the folding temperature, then the folding is most efficient, because under those circumstances, it's extremely unlikely that the protein would populate anything that would hang around long enough for aggregation to actually proceed. One other thing is that this transition from high temperature to T theta is nominally thought to be second order. It's continuous. Free energy is continuous, only whereas this transition, in fact, is first order, but mildly so. It's not strongly first order. It's weakly first order. And that's because, and this is one of the crucial differences I'll point out between the nucleation we heard for the last couple of days and this problem that the barriers between the folded and unfolded state are not nearly as large as you would to nucleate, for example, a liquid droplet in a supersaturated vapor. And this is basically first order, and therefore if this parameter is small, then the efficient folding occurs when these two lines meet, and that's what one would call tricritical point. Shri.
So this is weakly first order because of the finite size?
It's partly related, it's almost largely related to finite size, and also because of the nature of interactions that are stabilizing the folded state with respect to the unfolded state is not covalent or not that strong.
Okay, okay. So just for curiosity,
Again,
what's the largest single domain protein that one has?
Yeah. So usually, if I look at the genome of E. coli, there are about 4,000 some proteins, and the length distribution, the maximum is 200. GFP, for which there was a Nobel Prize, I think, 2 years ago, it's a single domain protein, and it's got about 250 residues. You can basically show, and this is an argument, you can show that if it exceeds beyond that, it's better to create a multi-domain protein with an interface, although you're paying the interface cost because of the stability reasons. It's about, say, 200, 250. That's a maximum. So what about the size of a protein? So I'm going to tell you about the Flory laws. And the point is that you can go far into this game without really knowing a lot, and that's what the physicists actually like. Right? So that's really what I want to tell you for the beginning. But believe me, that's really not the real thing to do. If you really are interested in biology, you really got to come to grips with all the specifics, and it took me a very long time to do so, but I was glad I did so that I could talk to all these guys who have wonderful problems in their hands. So if the unfolded state that you created by adding, say, denaturants is indeed a good solvent, in the sense Flory told us, then you expect the Flory laws to be valid. The radius of gyration must scale as the number of amino acid residues to the power nu and times the prefactor. And the nu is given by 3 over d plus 2, so in 3 dimensions it's 0.6, roughly speaking. So this is one of the important things that you should actually remember if you want to estimate the dimensions of a polypeptide chain. Yeah? Coming. Just 1 second. If the folded state and the collapsed globule are maximally compact, then you expect the radius of gyration should scale as n to the nu times its prefactor, and this means that the solvent is poor. Usually, for most proteins, neutral pH for water at room temperature is a poor solvent, and Rg will scale as this, and nu will be 1 over 3, or 1 in 3 dimensions. So how good are the Flory laws for proteins? And that'll answer the question about what these prefactors are, and I'll also tell you some slight numbers associated with the persistence line. So these are experiments in a log-log plot done for unfolded conformations, generated largely by denaturants, but sometimes by temperature. And it turns out that the unfolded state, you can fit this as 2 angstroms times n to the 0.6. The 2 is a very small number. The persistence length, in a strict sense, is about 2 to 2.5 times larger, it's about 5 angstroms typically for a protein. And just to calibrate the number, you know, double-stranded DNA, the persistence length is about 50 nanometers. Single-stranded DNA or RNA would be 10 nanometers. And this is only 10 angstroms, I'm sorry, and this is 1/2 of that. And things like microtubule and actin have persistence lengths that are gigantic, right? Microns and longer. But the Fourier law is obeyed in some sense. It fits pretty well. Only very recently, I mean 6 years ago, people produced this plot for using, people mean this person who is now a professor in Cincinnati, as a function of n, and this is the compact states. This is taking some thousands of structures that are in the PDB, simply computing the RG is a mindless job, in fact, in some sense. And in fact, it obeys Fourier's law. Not all of them are maximally compact, and this, in fact, is an important thing that will play some role later on. So they're largely spherical, which means that asphericity is small, but they're not maximally compact. So nevertheless, if you use this formula for any generic single domain protein, the error that you will make in estimating the radius of gyration is probably about 15% or so. It's a damn good formula to remember. Okay. I'll come back to this graph again. So how do I want to view the folding, where it goes from something which is expanded in this sense to something that's compact, but because of the finite size, you really should not think of this describing this folding reaction in terms of a single order parameter, but what you really should think about is change in the distribution function that is characteristic of a protein. So you really should think of folding as changes in the distribution function, but distribution function of what? Here, for example, is the distribution of radius of gyration. These are really calculated for this protein, which is protein L, by my former student, as a function of gonadinium concentration. Unfortunately, I won't tell you how to produce this because we introduced a very new method for actually computing these quantities. And you look at this at this is 7 molar gonadinium chloride, and you see only the large RG values are populated, whereas if you go to 0, it peaks around this particular value of about 12 angstroms or so, and that's the radius of gyration that you'll calculate if you take the PDB structure for this protein L. And you see that the distribution of radius of gyration changes continuously, in fact, from going from high denaturing concentration to 0 denaturing concentration. There is no discontinuity of any sorts when you view this folding transition in terms of the changes in the distribution of RG, the radius of gyration. So with that, and with RG sticking in our head, let's think of an autoparameter description, if you want, of the folding reaction. Now, nominally speaking, you have the unfolded state and the folded state, but also you can imagine having this collapsed state which is not fully folded, in the sense that it hasn't acquired the entire native interactions. So with that in mind, you would minimally require to distinguish between 3 quote-unquote phases, unfolded, compact, and native, 2 order parameters. One of them could be, and these are not by any means unique, one of them could be the density of monomers in this sphere RG. So I define the density, which is number of amino acids divided by the volume occupied by the protein, which is RG cubed. If you want, you can put in 4 pi over 3 or whatever. And then a measure, which is the overlap function, is how much a given conformation, how does it resemble the folded state? These are the 2 order parameters that we can think of. There are many more, and I'll come back to that later, which is in fact the problem. So let's look at unfolded collapsed globules and folded states. For unfolded state, rho is small. Why? Because RG scales as n to the 0.6, RG cubed will be 1.8. So rho will be 1 over, it'll be n to the minus 0.8. For any typical value of n, the rho is going to be small. Chi will be large. The way we defined it, large chi means that it has very little overlap with the native state. We should have done it the opposite way, but that's not the way we did it. And the small chi means it is exactly the same as a native state or the folded structure. If you want, you can think of this as a vapor, a low density fluctuating object, which is kind of like a vapor, if you wish. This is a globule, collapsed globule. The rho is expected to be of the order 1 because RG in fact scales as n to the 1/3. So rho is of the order 1, but chi is still large because this is a compact object that's fluctuating, still not exactly the same as what the native state is. That's a second order parameter that you can think about, and if you want, you can assign that to be a liquid. These are all loose way of association, and the reason I bring this up is because you've been inundated with this language of nucleation for about 10 days. So the other one is the native basin of attraction. Here, of course, is maximally compact. Rho is of the order 1. Chi is small because it's in the native basin of attraction, and therefore this you could think of as a dense, ordered object, kind of like a solid, although it's not really a solid. So there is a loose analogy between vapor, liquid, and solid, and possibly the unfolded coarse grain, collapsed globule, and the native state. So with this analogy then, one might think that you should be able to develop a nucleation picture. After all, when you have conditions that are favorable for the folded state to form, it may nucleate something, embryo as the word was used yesterday, of the folded state, which then would then suck, once that's formed, there's an overwhelming possibility of getting to the native state. So yesterday we learned in a very nice discussion that if you want to think about free energy cost of creating a droplet, this is what you would write down. This is a driving force, which is the chemical potential times the size of this object to the cubed, and something that opposes that, which is a surface tension term. So this is in every nucleation picture, and we heard lots of examples from David yesterday and some today from our morning speakers, that this nucleation basically always has a driving plus opposing force. For reasons that are pointed out yesterday, which become even more severe when I pose this in the context of the protein folding, none of these numbers, in fact, are constant. We don't know exactly what the driving force is. Certainly, surface tension is not really a constant, and these are problems that exist in writing down something as simple as that. Even in the homogeneous nucleation theory, we knew from yesterday that to assume that these droplets are spherical is not correct, and in fact, there are fractalities associated with that one must worry about in the context of protein folding even more. Here, the driving force is, nominally speaking, a hydrophobic collapse. The hydrophobic residues want to be clustered in the interior of the protein and exposing the hydrophilics, which are on the outside. So that's one driving force. But we also learned a little bit, and this is increasingly becoming important, that there are many cases in which the burial of hydrogen bonds is a driving force, and there are no easy ways to write down energies in terms of this droplet-like picture in the nucleation picture for folding, although I'll show you some tentative attempts to try and do that. What is opposing the formation of this native state is entropy loss due to looping, and the fact that just like here, you might have to create some sort of a surface compact object, and that is related to surface tension, but with the droplet with the non-constant gamma, and this is sort of something that also is relevant in the glass formation. So I'm going to describe to you some tentative models, and then I'll describe some slide.
Due to looping, is it just the fact that you have a heterogeneous surface?
No, the fact is that it's a polymer chain, and then if I bring some piece together, I'll necessarily form some loop, and that's a loss in entropy because it forms a loop, and I got to worry about that. That usually in the polymer for large N goes as logarithmic of N, and you don't worry about it, and I won't worry about it here. But although you should think about it, and for short chains, it can make quite a bit of difference. Okay? These things, oh no, I can show you in the picture here. So if I look at this picture here, see these two are ordered, but there's a loop connecting that, and the loop in fact would be, well, she's getting an explanation from the side there, so I'll leave that alone. So I just, yeah, it's okay. It's much less important. Well, anyway. So the way I want to develop this tentative nucleation picture, it's only for Shree's sake that I'm talking about nucleation. We did write a few papers on this, but not our main gig actually. So we want to talk about creating a cost of creating a region where NR residues or a total N are ordered. Just exactly analogous to the droplet picture, where you're creating a droplet of radius or of one phase, the liquid phase, say, in a supersaturated vapor. What is that? That's what we want to ask. So then you can imagine, because of these two opposing forces, it's likely, it's not super clear, it's likely that if I plot the free energy of creating such an ordered region as a function of the fraction of residues that are in fact ordered, you would have something as a barrier, just like in the homogeneous nucleation theory. However, you know a priori there's a distribution of radius of gyration. I showed you that. And therefore, this landscape cannot be so nice as I've drawn it here, but it's got to have some ruggedness associated with the fact that there could be structures forming everywhere, because fluctuations within that nucleated structure with NR residues can be very large here. I'm going to refer to this as a multiple folded nuclei model, and there are many such nuclei that you can form anywhere, in fact, in principle, as long as you don't violate topological restrictions. That's the only requirement that I have, and I'll call the multiple folded nucleus. This barrier is here shown to arise early in the folding process, which means if I sit here, the fraction of residues that are ordered is less than the fraction of residues that are ordered here, and this may correspond to some diffuse nuclei. For whatever reason, topological restrictions, the nucleus, in fact, forms only very close to the folded state. So these are all questions that people, in fact, want to ask. The related question is, which is also asked in the nucleation game is, and we had some discussions of that yesterday, that if I look at the embryo of a solid nucleating in a liquid under below melting conditions, what is its morphology with respect to the underlying registry? And David, in fact, answered that can be anything. It need not be, say, FCC. It could be something else, even though the final ground state is FCC. So there are issues like this, and therefore, what is the nature of these structures that are populated at the top of the barrier? That's what I'll define as a transition state ensemble. How does that actually look like? Because that I'll answer only in numerical terms. So this is our pure phenomenological model. Remember, I don't know how to write down very easily what my driving and opposing forces are. One picture of this was to write down the free energy cost of creating NR residues that are ordered is something that goes linearly with NR. I'll tell you the rationale for that. And then the surface area term, which undoubtedly is not correct, which just follows from the homogeneous nucleation theory. The reason this delta F, which is analogous to the chemical potential that you're familiar with, is the amount of free energy gained that will be gained by a residue that forms a native right contact with respect to the unfolded state. Seems pretty reasonable to write this down. So that's the first term, and this opposes that. So you do the usual minimization game, then it says that there is the critical nucleus in this picture goes by this little formula, and there are some numbers that are available with very large error bars for gamma and smaller error bars for this analog of the chemical potential. When you put them all in here, this number turns out to be very large for whatever reason. So this can't really be NR, it's probably going to be something less than that. We said, this is our stuff some time ago, we said, look, the driving force really is hydrophobic collapse, and if I create, yes?
What value, I mean, how do you define gamma over here? What values do you put while trying to calculate NR star?
I'll tell you the value and I'll tell you how it's obtained. These are from experiments. The value is 25 to 75 calories per mole angstrom squared. Okay? The way it's obtained is to ask, you transfer an amino acid residue, which has a dimension roughly R, from one condition to another condition, say from some organic solvent to water, and you ask, what is the free energy cost of transferring that? And from there, you obtain this surface tension value. Okay? Very crude, and this is really not the value that you should actually be putting at all, and this is one of the problems that I'll repeatedly mention is something we don't know how to do. No, it's correct. That's a free energy transfer, and then for that you subtract out of the cohesion energy. What's left over is what is done. So it's a little bit more involved analysis, but that's a basic experiment. And people have also even tried even for this little object. So remember, these objects are going to be of the order of about 5 to 7 angstroms, even Tolman corrections and things of this kind. So, right. So the second picture, phenomenological way, this is another extreme, is that the ordering is driven by hydrophobic interactions. So if I take a region containing NR residues, and I then ask maximum number of hydrophobic contacts, that'll go as NR squared. This, of course, is overcounting that, because this is like a extreme mean field analysis, and then this is the average strength, if you wish, and then once again you play this game, and this produces a number of the order of 15 or so residues, and we actually worked very hard trying to get some experimental data on this 20. So the point is that these numbers, the nucleus size is of the order of 10, 15 or so. That's a point. That's what these guys predict. You should not take any of these theories very seriously, except as a ballpark estimate. So, but the interesting thing is that you can in fact see if with these numbers that you have on the locations of this transition state for some specific systems, you can do a computer simulation. These are computer simulations of simple models. One of the other things that I should say is that the barrier from here to here in homogeneous nucleation theory is very, very large, and that's why nucleation rate is quite small. But here the barriers are relatively small. In fact, I'll argue later it only scales of square root of n times kBt, because if the barrier was really very large, folding time would be astronomical. That we know is not the case, and therefore these barriers are relatively small. That's one thing. With this picture in mind, you can go back and do a computer simulation of simple models, because in order to do complicated models in an all-atom simulations, you cannot produce huge numbers of trajectories, whereas you could in the simple models. And then you can ask questions like, what do these quote-unquote nucleus, what does it look like? Is there something unique about it? And you can correlate this with some definition of transition state, which I'll come to at the end. So those are the next things I'm going to describe. So we generated folding trajectories for these two models, very simple topologies. Their secondary structure connectivities are different here. You can just read them off here. This is 2 strands, S1, S2 followed by a helix, where the helix is in between these 2 strands. So we are interested in asking some questions. Does topology of the connected secondary structures affect the nucleus, etc., etc.? So we created these. So this is a horrible picture, and it's does not even correspond to the Brownian dynamic simulations of the 2 structures that I showed you in the previous slide. It's a lattice model. The only point I want to make is the following. These are just like Surjit's, except that I think you can see the lines from back there, but they're just as bad. So these are 2 different folding trajectories created for this lattice model, in which you go to high temperatures, and presumably they're folded, but you know everything about this system. And then you run the simulation until it reaches the folded state for the first time. So that's the left-hand trajectory, and this is another one. There's an independent trajectories. And by eye, you can tell that these 2 trajectories are very, very different. So we know this. That implies, and you can do this hundreds of times, that there's a large heterogeneity in the folding trajectories, which means that whatever processes that govern the formation of this structure at this end in this trajectory has to be somewhat different. And if this is quote-unquote nucleation in some sense, the nucleus that you would identify in this trajectory is different from a nucleus identified in that trajectory. And of course, a nice way of saying this is there is no such thing as an average protein. Every protein molecule is in fact special. Okay? So it's a specialness that we want to tease out in doing these sorts of trajectories. This is back to the models that I showed. The way we search for the nucleus is exactly the same as the way people like Ray Mountain and Hans Anderson, I think in the 80s when they were running this 100,000 particle simulations to look at nucleation would do. You follow the system till it crystallizes, And so you have the entire record of the system. Then you go back in time to see where the embryo actually formed and was stable, and then you start looking at that for various trajectories. That's what we do here. So in the inset, there is a progress variable that tells you how far is the folding reaction gone and what is the probability of really reaching that native state in terms of this progress variable. And you see it's pretty much 0 till this progress variable reaches some value, and it suddenly goes up. So something interesting is happening here on an average. It is that region we then say it must correspond to the barrier crossing, or in which you could have embryos of the native structure present for the first time. What is shown at the bottom here is you run, in this case, 100 trajectories or so. For each trajectory, we devise a neural net type algorithm that identifies this region, freezes the snapshot of that point, looks at what are the kinds of structures and the contacts between the residues that are present in that state, and then there's an average of those over here. So what is plotted here is a probability that in this quote-unquote transition state region, which will identify as the close to the barrier top, although there are lots of ruggedness on top of that, probability that this nth residue in this chain has native-like character, the folded character, as a function of the location of that chain. That's what is shown here. The 3 colors are 3 different regions, so we might as well just look at one of them. So there are 3 values of this coordinate that monitors the folding reaction in this region. So we'll look at delta equals 0.95, which is a blue color. What this shows you is there is not a single residue in this transition region that is formed with unit probability. The maximum is just about 0.7 or so. This is 0.7, 0.7, say it's a 0.6, and so on and so forth. If you say that the relevant residues, which are important or have high probability, let's say it's greater than 0.5, you would say these are the set of nuclei here. Okay? That's your nucleus, if you wish. And it's an average nucleus because I've averaged this over a number of folding trajectories. Number of folding trajectories, and there's nothing unique about this nucleus, if you wish. And this picture resonates with the kinds of stuff we heard yesterday, because at the nucleus, you really don't have even complete FCC solid if that's the ground state. You could have some other pieces, and that's really what you find here. So there are multiple folding nuclei, and all you can say is that each residue has some probability of being formed at this transition state, and you have a heterogeneous set of structures corresponding to the barrier maximum, or at least at the place where this progress variable takes off. Okay? And this, of course, shows the same thing, but it tells you how important the secondary structure connectivity is in the native state, because this pattern, in fact, does not look like this pattern at all. By merely changing the topology in this particular example, I've altered the transition state ensemble completely. There's one other question I need to answer to nail this as a transition state, and that is to use a definition of what do you mean by transition state. There are lots of definitions of transition states, and one of the definitions of transition states is it is a surface in the multidimensional space across which the flux to either the unfolded state or the folded state is roughly equal. In other words, if I started the ensemble of structures, these are my ensemble of structures at the top of the transition state, and I ran simulations, they would have 50% chance of going to the native state and 50% chance of going to the unfolded state. If this is roughly satisfied, then I identify this as a transition state ensemble. This definition incidentally goes back to Lars Onsager, which he called it the splitting probability that he talked about, and he worked out some simple methods for computing that. So that's the next thing we're going to do. Before that, I say this structural plasticity to show that you can alter these things very, very easily. Oh, no. So what, I don't have a graph of that. So what we then did was to do exactly what I just described, start new simulations sitting on top of the barrier. I don't know if it's top of the barrier corresponding to these structures, ran the simulations, and as reported in the paper, you'll see it's about, roughly speaking, I think it was like 55-45, and given the finite size and so on and so forth, that's not unreasonable. So from this generic idea that there may exist a nucleation for which you could write down something which is probably wrong, not probably wrong, but the unit probability wrong probably, and that you can get some picture of how these embryos actually might form in different places with different probabilities, but then cumulatively they constitute a set of structures that correspond to top of the barrier, and we know that they split with equal probability to the right hand side. So we sort of nailed that picture more or less, period. How should we improve this in some sense? This is really hiding ignorance. We were confidently writing that the driving force has nr to some power, either linear or square or something like that, but we really shouldn't do that. I now remember that there was a small mistake in my nr, but it's okay. And we also thought that this object is maximally compact, which is clearly wrong, because if I look at a protein which is an unfolded state, it's definitely a fractal, right? And even if I look at the unfolded structures, it turns out that the nu is not 1/3, it's got some fractality associated in the folded state as well. So being totally ignorant about all this, the free energy cost that you should write down is some coefficient alpha 1, don't know what that is. Nr to the power of delta is an exponent, and this to the power of theta. Theta is 2/3 corresponding to the usual stuff, which is not quite correct. Theta probably could be 1.2 is a better number actually, which is the unfolded state, but it's certainly not 2/3. If delta is roughly equal to theta in this expression, or these are these loop corrections that I talked about, the entropy of loop corrections, let's ignore that, then it turns out that the barrier is going to be very, very small. And in fact, there are proteins for which the barrier is only of the order kT, and these are called downhill folders. And my good friend Victor Munoz, in fact, has shown that the BBL protein that he works on has very little, or at least kT barrier, and still can be described by this kind of picture. We don't know what delta and theta is except for upper bounds. Surface tension certainly cannot be constant, because if I look at a single molecule whose nucleation I'm talking about, when it orders something, its surface tension is going to be some value. I'd look at another molecule a little bit different, but I don't know how to compute that very easily. Incidentally, since Sri has woken up now, the same scenario occurs in a theory of glass transition, where the surface tension is not really a constant, and there are domains and boundaries. This is a kind of a picture. They're present everywhere, and you have a non-constant surface tension. So one has to worry about this. And in fact, in response to your question, I basically pleaded ignorance in some sense, because you really got to be careful in defining what the surface tension is. And if any of you want, you can do some numerical experiments at the very least to figure out what this should be. So this got to be fixed. There are multiple folding nuclei, and that implies structural plasticity. But this is a starting point with which you can work with in terms of unknown exponents and put bounds on it by comparing with some experiments, and that's what we did when I quoted you the number 27. And I think the theta value in our case turned out to be 0.7 in that case, and I forgot what the delta value is. Okay? I'm going to stop with the nucleation part there. I'm going to do something else now, right? Am I supposed to ask, are there any questions or what? So I'm asking, are there anything? Any questions? That gives me some opportunity to drink some water.
Yeah, so like the protein folding actually depends on what kind of solvent you have, right?
Absolutely.
So do you lump the contribution of the solvent into the surface tension? Or
and the driving force as well. Yes. Okay. Yeah, in this picture. Yeah, so it's a good question, right? And this is the reason why card-carrying protein guy doesn't buy these pictures, because that's exactly what they want to know. They want to know, how much contribution is coming. Don't tell me this in terms of deltas and thetas and alphas. And so they want to know a bit more specific. So do I. I'm now gone to the dark side. I'm with them, actually. I too want to provide those answers. This was good for me when I was starting, but now it's not good for me.
So when you're identifying the different residues that are in each of these heterogeneous nuclei,
Yeah.
are they locally connected to each other, or have you just got, are they just spread out?
That's a good
Around the
question,
protein.
actually. That's a very good question, and that depends on the topology. So what Richard is asking is that are all these nuclei residues in this NR droplet very close to each other in space? That's for sure not close to each other in sequence, and the answer is not necessarily. There's a balance between quote unquote this longer range and the shorter range, and it changes from trajectory to trajectory, and that's why you get the average picture. And it also depends upon the topology, and therefore it is in a material science sense as rich as the kinds of stuff that Surajit was talking about, perhaps even richer. Okay? I'll go on, right? Right. So David, now I know what you mean by, you better buy me a drink after this, man. I'm telling you, this is deadly stuff. I'm now going to tell you about something which, again, in the spirit of being physicists, the only universal thing that we have ever discovered in the context of protein folding, and hence not of relevance to biologists. I don't blame them, incidentally, but like I said, I've gone to the dark side myself. And this has something to do with the finite size effects on folding, and also related to the order parameter description. These are all experimental data, 3 proteins. One is ribonuclease A, that's the largest protein in this in terms of N. And the second one is Willen headpiece. Willen headpiece is a protein that's becoming extremely popular in the United States because there are several groups who are trying to use all-atom simulations to fold this repeatedly, and it's a small 35 residue protein. And this one, I forget what it is, but it's somewhere in between. What is being plotted here are experimental data, and if anyone is really interested, I can tell you how to get this. The fraction of molecules that are folded is a function of temperature. At very high temperature, of course, most of the molecules are unfolded. At low temperatures, it goes to unity. Roughly speaking, this has been normalized. If I look at this, this dash curve, that's this piece here, you can just by eyeball tell that this is the least cooperative in some sense. It is not as sharp a transition as, for example, this dot dash and this green guy, which is very cooperative. It goes like that, right? Okay. The other curves are all derivatives of this curve to get an indication of the full width at maximum. So for the Willen headpiece, the width of the transition is quite large. It's smaller for this protein. I think it's a 4-helix bundle, and this is ribonuclease A. So this is the kind of data that you would get. Mostly, though, you get data as a function of guanidinium concentration, because it turns out temperature is not the right way to do these experiments. Well, it is a good way to do these experiments, except most proteins, in fact, aggregate at high temperatures, so people typically use denaturants. So you can use the same thing as a function of denaturants, and I'll talk about that in a second. Yeah, I think that I've never defined this quantity anywhere. Let me see. No, it's there. So I'm going to show you 2 results. One of them, in fact, follows from thermodynamics rather trivially. The other one less so. And so there's some subtle arguments here, and I'll try to go through them as carefully as I can. I will introduce a dimensionless number which tells you how cooperative a transition is. Okay, and that comes as 2 slides from now. And we want to get a theoretical estimate of how that cooperativity scales with N. This is published in PhysRev letters for 6 years ago, I think. In order to do that, I'll introduce a quantity. I already did, actually, the overlap parameter. And the way you identify the folding temperature is it's a maximum in the susceptibility, delta chi, which will be just chi squared average minus chi average squared. And chi is this overlap parameter, which tells you how similar a given conformation is to the folded conformation. This is really like susceptibility in magnetic systems. And you know the susceptibility in magnetic system can be written as a temperature times the average order parameter with respect to some ordering field. right? You can write this. These are two same things. It's linear response. In the ordering field is the magnetic field in spin systems, say. And here delta chi is dimensionless, so I can say that the ordering field here must correspond to temperature itself, or in the presence of denaturants, it corresponds to the denatured concentration. The second argument is that the efficient folding, the melting temperature, which is kind of like the first order transition, or the folding temperature, must be close to the collapse temperature. And this is a result coming from a paper in PNAS some time ago. And therefore, the properties of this dimensionless function, which I've not yet told you what it is, must be controlled by the properties of the protein in the denatured state when you come to the folding temperature from above. Okay? If this is correct. We know from Dejean's work that, in fact, you could say that the RG near this collapse temperature must go as this width of this transition that I showed you in the previous graphs, divided with the temperature to this exponent nu, and we already met nu before, that's a Flory exponent. So RG must go into the nu, that implies that the width of the transition divided by the melting temperature must go as 1 over n. This, of course, is a thermodynamic statement that the transition becomes sharper and sharper as n increases, and this is really a finite size corrections, if you wish, to the melting. Is this correct? If this is not correct, we should go home. And so this is a logarithm of this quantity as a function of log n, and these are for lattice models of side chains. Who cares about that? So these are temperatures, and roughly speaking, this is 1 over n. It's 1 over n. A little bit of a caution here. These data points that are obtained from literature experiments were conducted in laboratories all over the world using all different protocols and different kinds of error bars, and these are not the most carefully done experiments in the critical phenomena sense. If you did that, there is no question this will fall on this line, but nevertheless this correlation coefficient is quite large in fact. So we check this out. So now what is this dimensionless quantity? It is just equal to the melting temperature squared times the height of the derivative of this order parameter, if you will, with respect to temperature at Tm divided by the width of the transition. That's what this is, and this is dimensionless. The reason we constructed this dimensionless function is that you could compare simulations and experiments done either by changing temperature, guanidinium, or even force on equal footing. Very easily you can see that if the transition was infinitely cooperative as it would be in an infinite system, this would go to infinity, whereas if it were not, then it will be small. And so with this definition, we are good to go. This guy is just TF over delta T, and we show that delta T over TF is 1 over n, and therefore this goes as n. So this is linear in n. This piece in here is the susceptibility, and because the susceptibility properties are governed by, I gotta stop. So if the properties are governed by the susceptibility, as you come from above, then you know that they have to be governed by the properties of the polymer chain or the protein chain under good solvent conditions or nearly good solvent conditions. And we know susceptibility scales is, again, this is from polymer stuff from Dejean. Delta chi scales as n to the gamma. Gamma is a susceptibility exponent, not the surface tension. Okay, sorry about that. Putting this together, we predict that the dimensionless parameter must go as n to the power of zeta. Zeta is a universal number which is 1 plus gamma. Gamma in 3 dimensions is about 1.2 or so, and therefore you expect this to go as 2.2. This is totally universal. It's an unbelievable thing that when specificity of proteins in fact governs most of its function, we discover a totally universal relation which is independent of various conditions. The question is this correct? And of course I won't be telling you if it isn't. This is a log of this parameter as a function of log n, and these are the same proteins for which I showed you delta t over t goes as 1 over n, and here it goes as n to the zeta, and the slope in fact is 2.2. This is for lattice models where you could do some precise calculations. And so this is a universal forget about the inset. It'll take me a little while to think about that. So, okay, so there are some finite size effects that one can capture. There's more to the finite size effects, which again brings in my good friend Victor Munoz at some point. So I want to now go back and think about folding again a little bit, because this will make a difference. This is one way of looking at the folding reactions. I've already described to you in terms of the radius of gyration, but we can also think about other things, and so let's think a little bit about autoparameter descriptions of phase transitions. You guys know, being physicists, know a lot more about this than I do, but let me just briefly describe that. If you have a macroscopic system, like a magnet, you have basically magnetization is a good autoparameter. It's 0 in the paramagnetic phase, and it's non-zero, and that's it. In weakly phase order transitions, like nematic phase transitions, P2 cos theta, how the molecules align themselves along the director axis is a good autoparameter. And synectic phases is a bit more complicated. You have to think about tilt angles and so on and so forth. And there are, each time you have this ordering, corresponding to the autoparameter, there's a rigidity associated with that, and there's a stiffness coefficient associated with the ordered phase, nematic phase, and here you need about 3 elastic constants to actually describe that stuff. Spin glass is a bit more complicated. You need 2 autoparameters, much like the folding reaction. One is M itself, and the other one is a so-called Edwards-Anderson autoparameter Q. M is 0 and Q is 0. That corresponds to the paramagnet. Spin glass phase, M is still 0. No average magnetization, but the Edwards-Anderson autoparameter is non-zero. And in a ferromagnet, they both are non-zero. Therefore, one knows intuitively you can't derive these autoparameters, but the physics, in fact, dictates for you what is an appropriate autoparameter. And if you have an autoparameter, you write down Landau's Ginzburg functional, and then you turn the crank, reading lots of books, etc., and you can describe certain things. Let's look at these proteins on the other hand. I described to you 2 autoparameters that can in fact distinguish between these 3 phases, and we should say we're good to go. But nobody told me these are unique autoparameters. I could insist, by looking at the native structure, that my autoparameter should be helix or sheet content, distribution of contacts between various residues, distribution of helices, anything that you can think of should be the description of the folded state, and therefore unless you measure my autoparameter, I won't agree that the molecule is folded. This may seem like a silly intellectual talk, but in fact it has got real consequences, because you can use different experimental measurements for these different autoparameters, and they might tell you slightly different things about the way ordering actually takes place, and that's what I'll show you both experimentally and otherwise. So this is an interesting story. That's a lesson that you should always talk to everyone who's interested in talking to you, because they might tell you something that's very important. So I was visiting St. Louis, Washington, St. Louis University. I don't know, this is many years ago. It's definitely prior to 2002. And there's a guy called Al Holzer, who is retired. Perhaps he comes in very rarely, but he wanted to see me. He was last on my schedule. It's 5:30 in the evening, and I was exhausted, and I go in his office. He pulls out this large binder with huge number of transparencies. For those of you in the students who don't know what a transparency is, this is how we used to give talks when we started. You write them down, there's a projector, etc., etc. He's flipping through one of these, each one at a time, and about 10 minutes into this, I'm literally falling asleep, much like the way Dave Weitz was throughout his stay here. Literally. And he must have noticed this, and I'm just nodding my head. But then he comes to one particular slide, and I'll show you that slide next. And he tells me something, and then he moves to the next one. And I wake up and I say, well, come on, let's go back to the previous slide. And he shows it to me, and I'll tell you what that slide is. And this paper that I wrote is a result of that slide. So this is not so important as the experiment itself. So let me show you the experiment. Let me describe let me tell you what this is. This is just a lattice model with side chains. This is in this paper, and we looked at the temperature at which every single residue in this lattice model, it can be very precisely done orders. Okay? And that is the fraction, the temperature at which the fraction corresponding to the ith residue is equal to 1/2. So half the time that's fully ordered, half the time it's fully disordered. That's the melting temperature of that particular residue. Because in the native state, I know that this particular residue makes contacts with its neighbors and so many of them, and if it does it 50% of the time, I assign that. And that's how it's done in the experiment as well, roughly speaking. And if I plot that melting temperature as a function of I, you can see this. You see there's this dispersion. It's not really a constant, as you would think if there's one unique melting temperature. And this is really a finite size effect consequence. So that's what we showed and we wrote about this. But this is more important. This is whole. It's the same sequence, and we know in the native state, a given residue, say alanine is in contact with leucine and so isoleucine and something else, and there are 6 contacts or 4 contacts or whatever. And we ask, what is the temperature at which there's a 50% probability of that residue being ordered as it is in the native state?
So it depends on where you look at the
Exactly. That's the key point here. That's the key point Al told me. Al stuff. This is experiment. It's no longer a simulation. For leucine zipper, and it's a melting temperature as a function of residue number obtained by one-dimensional NMR experiments. And you can see this is not a constant. It varies from the smallest number is about 42.5 degrees to about 50 degrees. There's a 7-degree dispersion, which is not small, given that the global melting takes place somewhere here, say. So this says that ordering depends upon where you actually look. And this is quite consistent with what I showed you earlier in a kinetic sense, that you can only ask questions of probability, not certainty, which reflects the underlying heterogeneity in the protein conformations. Victor Munoz and my colleague David Fushman did an experiment in which it is really a super generalization of the experiment of the BBL. They sat in on about 100 or so protons that are present in BBL, more than that, and calculated the ordering temperature in much the same way Al Holzer did in 1997, and as a function of temperature, and this is a distribution of melting temperatures, and you find that this is about 300 something other is a melting temperature that you would report if it were just one melting temperature, but there's a large dispersion in this. And then they went on to make some deal about that. And this is really a finite size consequence. And this is another simulation from us from before. I must say that Giant, in fact, has done quite a lot of experiments dating to about 2000, in which he is actually also in agreement with this sort of picture that the ordering, in fact, depends upon where you sit, and the unfolding or folding does not take place as it does in an infinite system. So that's a direct consequence of that. So I started calling this the Holzer effect, but I think more recently I've started calling this Holzer-Munoz because Munoz complained to me about this. So, and I like Victor, so even though he went back to Spain. So this is the similar kind of computations done just to show this is not unique for protein L when you initiate folding by temperature or by urea, and this is sort of prevalent. And more people will accept, especially the kinds of experiment Victor, Giant, and others are doing, that in fact the folding is a lot more complicated than you thought in simplistic terms. Okay? All right, that's N. So now I'm going to, I think I'm going to skip this actually. It turns out that you could use N dependence for the folding times as well. So let me talk a little bit about colloidal globule transitions in proteins. So Giant the other day was talking about a collapse polypeptide chains as a precursor to acquiring the native state. And I think he's in the beginning stages of that work. But there are others who are also doing this. And these are experiments done by my good friend Gilad Haran in Weizmann. And this is protein L again. And the experiment goes as follows. So I'm just going to discuss the left-hand side. The experiment, you attach dyes at two specific points. I think these are attached at the ends. And just like the description that Giant gave, you measure Fred efficiency as a function of guanidinium concentration. And from there, Fred efficiency is integral of the Foster integral times the distribution of the end-to-end distance. They make a model for the end-to-end distance. From there, compute the radius of gyration. And that's what you find. Radius of gyration is a function of the guanidinium concentration. And you see this is really looks like a continuous transition. The molecule indeed does undergo collapse from an unfolded state, 25 angstroms. At the end, in fact, when you go to 0, it's a little bit less. It's about 16 or something like that. Okay, so this is a collapse transition. And there's some energetics that have actually pulled out of that. This is another experiment on cold shock protein, very similar to this. And this is from Bill Eaton. Okay. So now I'm going to describe some way in which you can think about collapse processes in proteins. Nothing in proteins is simple, and therefore collapse here is not just as simple as it is in a homopolymer, but let's look at what you would expect in a homopolymer. But this is not a homopolymer, it's a charged homopolymer. It's a theory that we wrote down for polyamphylites and polyelectrolytes. So let's just look at polyelectrolytes. First, let me show you the simulations. This is polyamphylites. So polyamphylites, for those of you who are not familiar with, are monomers, and in fact you can produce them synthetically, in which each monomer is randomly charged, and there's no correlation between the charges, although there in fact in general has to be correlations. And you can show very easily that if the net charge on that is positive, in fact it goes to square root of n, less than square root of n, it'll collapse, otherwise it in fact remains expanded. I mean, it's an easy argument to make. This is a computer simulation of a polyamphyllite with charge less than QC, which is square root of n times E, and it starts from an unfolded state, unfolded conformation, and it goes to this compact globule. Okay, you can look at the pair functions of this compact globule, and they are in fact arranged in a perfect BCC lattice in which the lattice sites alternate between your counter ions and the charged monomers. So it's really a piece of a small Wigner crystal. You can look at the same sort of thing for a polyelectrolyte. This is a polyelectrolyte with some attractive interaction, and in fact it undergoes a colloidal globule transition. And you can see from both of these things you form some clusters in the beginning, and then the small clusters start to grow, and once you form a large cluster, the large cluster starts to swallow up the small clusters until you get one final cluster. And the mechanism is basically the same in both cases. Here, of course, you have some kind of an order very similar to this both are in fact small pieces of Wigner crystal. The mechanism, in fact, occurs in two stages. The first stage is to form this very large cluster, and if you want, you can again, with pleasing my host Sri, call it a nucleation, and then accept that these guys have to be connected, and they have to, in fact, finally be engulfed. And the nucleation we predicted using theory, the time scale scales as n to the 4/5. It is topologically constrained, but you still form these big clusters that engulf the small clusters. Say,
but it seems to be happening by a phase separation type of route rather than nucleation.
I'm just talking about the monomers only. I'm not talking about the solvent, the monomers. And you know, but you're right that because of the fact that I cannot cut the chain, right? So there is some tension between the two clusters, and then they coalesce. It's technically maybe still non-nucleation. But the second growth, in fact, the second growth where the big guys engulf the small guys occur by, it turns out, by Lifshitz-Lyarsov growth, and with this alpha is roughly about 3. So we showed this roughly speaking. So there are two stages in which collapse occurs. The collapse problem, incidentally, is not only relevant in proteins, but has become increasingly relevant as a mechanism by which DNA packaging actually takes place in eukaryotes. And people claim, and there's a very nice science paper in 2009, that the DNA is in fact forming a fractal globule, which is not maximally compact, but compact, and the fractal globule has some advantages. Remember that packaging has to be reversible, and therefore you can't have knots and things like that, and they claim that's the way it goes, and that also is predicted to occur in two stages with two different time scales. That's why this problem of collapse is becoming more and more relevant. What about proteins? There are many scenarios one can think of for proteins. One is, let's consider these so-called two-state folders. I agree with Giant that there is no such thing as two-state folders, because I just told you there's a heterogeneity of interactions that produces even heterogeneous thermodynamics as far as melting is concerned, and therefore this can't really be two-state, but let's assume that it's essentially two-state. So we think that it goes from a random coil, and this is one kind of collapse that one can actually think about. Specific collapse on a time scale which is collapse time scale followed by folding time. What do I mean by specific collapse? Supposing...
What is the reference of your previous paper?
So what? Oh, this is Journal of Chemical Physics. Huh? I no longer publish there, so. Because I said I've gone to the dark side, so if you want to read my papers, you got to look at some other things. So what do I mean by specific collapse? Supposing you follow a trajectory, and then you follow the radius of gyration as a function of time, and it becomes globule. It becomes compact. Then you stop the simulation there and you ask, what does the structure of that look like? What I mean by specific collapse is that there are very few contacts that the various residues make that are not present in the folded state. Okay? There are very few contacts. That means most of them are correct contacts, and they then subsequently rearrange to go to the native state. These need not happen. You could have, in fact, many incorrect contacts, giving you just a compact structure with many non-native interactions. And I'll show you an example of that. So this is the radius of gyration squared as a function of time. This is a very old paper, and there are many newer papers. And you can see that this is a simple lattice model with just 25 or so residues as a function of time. And even here, the RG, in fact, does not decay exponentially, but there are stages in which it happens, and these multiple stages are the kinds of things that one needs to sort out experimentally, and this is a thing that I think Giant is quite interested in. So that's for a simple system. So what happens if you have a more complicated rugged energy landscape? So supposing you didn't have all these other competing bases of attraction, then any molecule that start from anywhere in the landscape would in fact go with sufficiently large probability to the native basin of attraction. That is not the case for these sorts of examples that I show here, and there are various other proteins, lysozyme, rubisco, the most abundant protein on Earth because it's in plants, and this is RNA. It turns out that and these are all experimental numbers, and there's a huge amount of literature starting from 95 to now that describe this so-called kinetic partitioning mechanism, in which we imagine some fraction of molecules, in fact, traverse this landscape very directly to the native basin of attraction, whereas many other molecules get trapped in many competing basins of attractions, and thermal fluctuations will have to assist them in overcoming the barrier on a longer time scale to go to the native state. And the values of phi, the fraction of molecules that fall directly to the native basin of attraction, ranges from about 5% to about 25% from the systems. They can even be smaller. Parenthetically, I note that for systems under which this phi is extremely small, these are called non-permissive conditions. And for those proteins, it is suspected you need chaperones to actually assist them fold before they start to aggregate.
So these are in vitro, right?
All these are in vitro experiments. So this is a jungle gym lattice model. So I'll show a little bit of that. I'm already getting tired, David. I don't know how you did the second one, actually. It's the second one. I might have to take a pass on it. I've got to speak much more slowly, I think. So this is a lattice model. I think it's a maximally compact structure. It's a vertices of a three-dimensional cube, 3 by 3 by 4. And these various balls in different colors represent different models for the residues. This defines a particular sequence. And this sequence will fold reversibly to this over and over again. You can change the sequence and still retain the same quote-unquote ground state. And you can then also make that fold as well. This we'll consider two sequences. One sequence has got this small value of sigma, which means the difference between the folding temperature and the collapse temperature is small, divided by the folding temperature small. The other one has larger value of the sigma, although they both have the same, topologically the same ground state, but they have a slightly different value of sigma, and therefore they're a bit more frustrated, and they follow this kinetic partitioning that I described to you pictorially in terms of the energy landscape in the previous slide. Then we want to know what kind of collapse processes are present in both, and then with that I'll actually stop. So if you look at the second sequence, in which there are only a small fraction of molecules that actually fold rapidly to the native state, whereas most of them fold by this slow track. And you can, in fact, this is a computer, you can calculate the time scales for both. What you find is that the time scales required for the slow trajectories, ones that get trapped in this competing basin of attraction, requiring thermal fluctuations to go to the native state, that time scale is about 100 times faster than the fast track processes. Okay? You don't understand? So you're looking at the ensemble of molecules that fold extremely rapidly. Maybe I go back to this diagram. Oops. So we are collecting all the molecules that don't get trapped in the competing basin of attraction, but reach directly here, and calculate what the average time for that is. That's what I'm calling fast track, and the others are slow. And I'm saying that the numerically, what you find is the time scale, the ratios of, oops, I'm going the wrong way. Geez. The ratios of those time scales of 100. Okay? All right. I mentioned to you briefly the lysozyme, in fact, falls in this category. This is the data from Sheena Radford. I think she was a postdoc at the time, and with Chris Dobson, and I don't know who this guy is. And they did this experiment. Actually, Kiefhaber was the first to do this, but this is an experiment from their paper in JMB in 97. And they looked at lysozyme folding, and lysozyme unfolded state to the folded state. They do find these fast track molecules, and this is just a ligand binding, so you really worry about this fast time scale, which is about 10 milliseconds, and you see that the slow is about 70 times greater, and therefore this is exactly what we find in a. You shouldn't be really so concerned that I'm not trying to match the lattice to this, but generically that this underlying mechanism of lysozyme folding follows this kinetic partitioning mechanism is the key point.
Are these backtracking proteins or?
No, they don't backtrack at all. It's just activated processes have to do something that misfold. I will now dissect the reasons why these things happen. The sequence A that I talked about doesn't get trapped in this kinetic, in this competing basin of attraction, and therefore all the molecules there, in fact, reach the native state quite rapidly. Okay. What is being plotted here is a radius of gyration as a function of time. These are all Monte Carlo. There are three curves in here. One of them is just a multi-exponential fit, and this shows you that radius of gyration compaction takes place in stages. There's a green curve and a red curve that you cannot possibly see from there. One of them corresponds to the sequence A, which folds extremely rapidly. That's a radius of gyration where there's no trapping in this competing basins of attraction. The other one is the radius of gyration compaction for the set of trajectories in the other sequence which does not get trapped in the competing basin of attraction. So the mechanism that underlies the collapse in the fast track of the sequence B coincides with the rapid folding sequence, and there are no defects in that. So this is like a specific collapse. And I'll give you evidence for that, for the specific collapse, a little bit more. This is the radius of gyration as a function of time for these slow track molecules, the ones that get caught in the competing basin of attraction. So even after this, so notice this time scale is 15 times whatever. This is 150. Even after about 10 times greater, it has still not reached the maximally compact structure because it has not fully overcome the barrier. So collapse cannot is impeded. Early events are similar in the fast track molecule and the fast folding sequence. The partitioning occurs. Okay, that's only for biochemists. Okay. So if I look at the native interactions, that's what N here means, as a function of time. That means I'm only monitoring the interaction formation as a function of time of all those ordering that's present in the folded state only as a function of time. Again, you see that the green and the red, one of them corresponds to sequence A, only fast track molecules. This is fast track molecules of sequence B. They obey exactly the same way. The native state is gained very rapidly, whereas let's come back to the non-native interactions. When you look at the non-native interactions, how much non-native interaction is in the compact state, you see that there's very little, or only 5%, 6% or something like that, native interactions in both the fast track molecules in the sequence A, whereas there are lots of incorrect interactions in the slow track molecules in the competing basin of attraction that had to be undone to fold this. So collapse itself is different in these two sequences. When one, it forms largely the specific collapse containing interactions that are already present in the native state, most of them, and in the other case, there are the heterogeneous mix of structures with varying amount of non-native interactions. This is what we refer to as non-specific collapse, and those non-specific collapse, the defects, if you will, have to anneal that take much longer time before folding actually occurs. I'm going to stop here. There's lots of experiments coming along, and I may discuss them or I might tell you something else after the break.